Since 1984, when I wrote an open letter to oral surgeons in response to a letter sent them by Nobel Biocare, I have been addressing the controversies and the misinformation related to dental implants that has been generated to promote the sale of dental implants. Here are 3 examples: a controversies brochure on implant connections and surfaces, an open letter to Nobel customers, and an analysis of Zimmer Dental's trabecular metal surface applied to the tapered screw vent implant. This January 2018 Clinical Research Associates survey of 1,120 dentists using value-priced implant systems from 10 companies showed that 54% of the dentists were using Implant Direct systems. Implant Direct was the dominant player in North America value segment of the dental market. These are some of the articles and journals I wrote while I was president of Implant Direct. I sold 75% of the company to Danaher's Cybron division at the end of 2010 and remained president of the joint venture through 2013, and then sold my remaining 25% interest in January 2014. Danaher acquired Nobel Biocare the end of 2014, and today Implant Direct is managed by Nobel Biocare's executives, so it can control the effectiveness of what was once its most aggressive competitor. In the next 44 slides, I will address many of the questions and controversies related to dental implant products and procedures. A common question is, what is the best design for the body of the implant? This slide shows wide variations available with different thread patterns, tapers, and designs of cutting grooves. Straumann recently introduced the BLX implant, designed by the same dentist that created the Nobel Active implant. The Nobel replaced trilobe implant without a cutting groove is basically the same design as it was when Nobel bought Stereos in the late 1990s. Implant Direct's Replant trilobe implant is surgically and prosthetically compatible with the Nobel Replace implant, but with microthreads and a vertical cutting groove added. The Nobel Active has a back-tapered neck, deep threads, and a 9-degree tapered body. The Legacy and Interactive implants, on the other hand, have a 2 to 3 degree tapered body with efficient long cutting grooves and a round apex. Another question is, what constitutes an effective self-tapping design for a tapered implant? Straumann's Bone Tap, similar to those of other companies, is designed with a flattened relief area that advances ahead of the vertical cutting groove as the implant rotates clockwise into the socket. The Legacy 2 and 4 implants have a long cutting groove extending up to the major diameter of the implant with a relief area similar to a bone tap. This is in contrast to the Nobel Active with its relief area trailing the cutting edge, so it's only effective for unscrewing the implant. The BLX implant has very deep threads that are wider than the top of the implant, and while its core is tapered, it is basically a straight implant. It has grooves cut through the threads at an angle, but without any relief area traditionally found in bone taps. Many companies contributed to the evolution of implant design, starting with the Straumann basket implant with its narrow neck of the 1970s. This led to the development of Corvent's hollow basket screw implant in 1982. By 1985, Straumann added threads and a full diameter neck to its hollow basket implant, but ended up violating the Corvent patent. After a court battle, they had to take it off the market for 6 months until we reached a licensing agreement. In 1990, Straumann switched to this straight cylinder screw that proved that a one-stage surgical protocol was as successful as burying the implant during the healing process. It took Straumann until 2007 before it introduced a bone-level implant. Here we see the new Straumann BLX bone-level implant with very deep threads that extend beyond the diameter of the neck of the implant. This is similar to the Megagen Korean implant. My first rule of implant design is that the widest part of the implant should be at the crest of the ridge to seal it. Wider threads can expand the opening to the socket as the implant is inserted into the bone, leaving a gap between the neck of the implant and the bone. This case shows the BLX implants inserted into the bone grafts following sinus elevation. The mesial implant is shown stopping 2 millimeters from full seating before inserting the distal implant to allow verification that they are relatively parallel. After the mesial implant is fully seated in the graft site, the narrow neck, having passed through the widened crest of the ridge, loses stability and is no longer parallel to the distal one. The image in the center shows, by contrast, a 10 millimeter legacy implant and bone grafting material elevating the sinus membrane. Its design with microthreads may be essential for achieving initial stability with only about 5 to 6 millimeters of the implant surface engaging the porous maxillary bone. Here is a case with 16 Legacy 3 implants done by Dr. Gary O'Brien. He states that, quote, "I just uncovered a case with 16 Legacy 3 implants and there was 0 bone loss on all 16. Very impressive surgical results. This is by far the most user-friendly, forgiving, bone-loving implant design I've ever placed," end of quote. I don't see any purpose in designing a cylindrical screw implant with a back taper to the neck like the Nobel Active, having threads wider than the neck like the BLX, or turning the cylindrical neck into a triangle like MIS's V3 implant, which I will discuss further in later slides. MIS's V3 implant turns the cylindrical neck into a triangle, claiming that this will help preserve a thin labial plate of bone. When the round drill cuts a hole that thins the labial plate, the damage has already been done. Having a blood clot between the bone and the flat surface of the triangular implant is not going to reverse that damage. A better solution is to use a narrower implant that does not require thinning the labial plate, or drill a smaller hole and expand the bone by the self-tapping insertion of a tapered implant. MIS cannot put the triangular shape on a small diameter implant because there's not enough metal. MIS's rationale for using its V3 implant fails in an immediate extraction socket as shown here, where a wider diameter cylindrical implant would have reduced the need for bone grafting material and allowed for a better emergence profile for the abutment and restoration. MIS also includes a final sizing tapered drill with each implant, but with a tapered implant being inserted into soft bone, the final sizing of the socket is completed with an intermediate drill. Another question is whether deeper threads increase stability in soft bone. Here is a marketing piece from Zimmer Dental that compared the initial torque of its tapered screw vent implant to that achieved with the Nobel Active, Nobel Replace, and Straumann straight bone level implant. The screw vent generated 100% more primary stability than the Straumann straight bone level implant and 29% more than the Nobel Active with much deeper threads. The deeper the threads, the wider apart they need to be, and this creates more space for the soft bone to push in as the implant is inserted. With shallower threads, the inner core of the threads compress the soft bone as the implant is inserted, self-tapping, generating higher initial torque and greater stability. I am no fan of the use of osseodensification drills that run backwards, supposedly compressing the bone as it pushes it laterally. Osseodensification occurs naturally by inserting a tapered implant self-tapping into an undersized socket, and the compacted bone is between the threads where it can do the most good in increasing stability. Is the cost of the implant directly related to clinical success? The answer is no. Here's a case where 2 Legacy 4 implants were used adjacent to a Straumann bone level implant. The U.S. list price for the Straumann components for the implant and abutment was $838 compared to only $230 for each all-in-one package Legacy 4 implant, which includes the transfer, abutment, and healing collar. Straumann introduced a bone-level implant in 2007, and it took them until 2014 to offer it tapered. Now Straumann launched a zirconia implant for $595. I don't know what problem it solves, but I certainly can see what problems it could cause. You can't change the angle, you can't change the margin, and you can't use it for immediate load because you can't use more than 20 Newton centimeters of torque during insertion, according to a UCLA speaker I recently heard. So let's talk about the question of all-on 4, 3, or 2 implants and whether to place the distal implants straight or at an angle to reduce the length of the cantilever extension. This is a Nobel all-on-4 case in the upper and lower edentulous arches with what looks like straight Nobel Speedy implants. Angling the distal implant requires the purchase of $250 angled abutments. This X-ray shows a case Nobel posted on Facebook or LinkedIn. If you take a close look at the distal implant, a radiolucency around the entire implant is evident. The bridge is holding the implant in rather than the other way around. That implant should be removed, and that would necessitate shortening of the bar, which is why it is prudent to place 5 to 6 implants in the edentulous jaw if bone is available, to avoid having to remake the prosthesis if one of the implants fails, as occurred here. Nobel has now launched its trefoil system using just 3 straight implants in the symphysis. This basically steps on their own message of all-on-4 with distal angled implants. There's a school of thought in Europe where they're putting in just 2 implants, as shown here. This zygomatic implant case was done by Dr. Ramzi Amin. If he can justify a long cantilever from engagement with only a small amount of bone in the zygoma, why do we need angled distal implants in a lower case to shorten the cantilever? Just put 5 implants straight up and down, as I show here graphically, and if you were able to do that, why not use one-piece implants like the screw indirect and save the cost and time of attaching the abutment? This is a case posted on Nobel's website using all-on-4, showing in the maxilla with what they refer to as the optimum implant distribution. Look at all this bone behind the distal implants. Graphically, I showed that there was available bone to place 6 straight implants. In my opinion, that would optimize implant distribution, building in redundancy and eliminating the need for angled abutments. The interactive implant was developed as a cost-effective alternative to the Nobel Active with many design improvements. For example, the Nobel Active has a back-tapered neck with micro grooves, while the Interactive has a straight neck to seal the crest on insertion and adds micro threads for added stability. The Nobel Active is tapered 9 degrees with cutting grooves designed to function in counterclockwise rotation to assist unscrewing of the implant when its aggressive taper results in it being wedged into dense bone. The Interactive has only a 2-degree taper, and its self-tapping grooves facilitate insertion in both dense and soft bone. This slide shows the bone loss associated with the back-tapered neck of the Nobel Active implant. My preference is to have a straight neck to the implant in order to seal the opening of the implant socket at the crest. This SEM of an HA-coated screw implant shows the transition from the SPM-blasted microthreads to the HA-coated threads of the body. The surfaces look almost the same. This case shows an internal sinus elevation with only about 4 millimeters of bone below the sinus floor. Having threads engage this limited height of bone will determine whether there is adequate initial stability for the implant to osseointegrate. This is where a micro-threaded neck may be essential for implant success. Back tapering the neck, as with the Nobel Active, or minimizing bone contact with a triangular-shaped neck, such as the V3 implant, is not beneficial. The disadvantages of a sharp apex versus a round one is the increased risk of tearing the sinus membrane if the floor of the sinus is perforated. A sharp apex can unintentionally result in changing the trajectory of the implant during insertion in soft bone from that determined by the drilling procedures. A number of implant systems only offer one diameter to the abutment connection for all diameters of implants, claiming the advantage of reduced abutment inventory. The Neodent, Straumann's Brazilian value-priced implant, has 5 diameter implants with just 1 diameter of internal shaft. In the case of Neodent, with its long lead-in taper, this requires long abutments and usually requires countersinking of the implant during insertion. These abutments with the Neodent wide implant create an undesirable emergence profile. This is in contrast to the legacy system's 7 implant diameters with 4 different abutment connection diameters to facilitate the optimum emergence profile. Straumann's new BLX system also offers 7 implant diameter options, but all with the same diameter abutment connection as shown here. Straumann recognizes the need for wider emergence profile abutments and offers them for the 5, 5.5, and 6.5 millimeter diameter implants, but these abutments sit on the top of the implant, abandoning the advantage of the implant's internal conical connection. Debate exists over whether the top part of the implant should be textured or smooth. Implant Direct, after I retired as president, launched the Legacy P implant with a smooth neck. But if you already have 100% success with SBM extended to the top of the implant and a documented bone loss of only 0.64 millimeters after 5 years, why look for something different? We know that bone tends to run down a smooth surface. As shown here, Nobel offers all different kinds of variations to the necks of its implants. With the Legacy implant having a very high documented success rate with very little bone loss, I firmly believe in extending its SBM textured surface to the top of the implant. This is a case done with the Legacy P implant launched after I retired and against my advice. In 1994, I developed what was called selective surface with a smooth surface on the top, smooth on the bottom for more efficient self-tapping, and SBM blasted surface in the middle. I've looked at all of these combinations and went with light blasted SBM surface over the entire length of the implant. Blasting with aluminous oxide like Straumann and titanium oxide like Astra requires a final wash with acid to remove the embedded particles. With SBM, which is water-soluble HA crystals, this additional procedure, which tends to round the threads and cutting grooves, is not necessary. Here is a study by Dr. Danny Boozer comparing Straumann's tissue-level implants blasted all the way to the top, with the same implants having the top 2 millimeters smooth. As reported in this study, quote, in general, implants placed with the top of the SLA surface above the bone crest had significantly less bone loss than implants with the top of the SLA textured surface level with the bone. End of quote. This indicates that a textured surface in the soft tissue does not contribute to bone loss. What is the best implant abutment connection? The internal connection with a lead-in bevel, first introduced in 1986 with the screw vent implant, is the cornerstone of modern implant design. Clearly, internal conical connections won out over external hex connections and over internal connections with butt joints like the Nobel replaced trilobe implant. Nobel now offers the replace with a conical internal hex connection. This external hex southern implant shows wear on the interface, and the company recommended 45 Newton centimeters of torque on the fixation screw to bolt the abutment to the implant, whereas most internal connection systems recommend only 30 Newton centimeters. Astra implants with an 80-degree lead-in bevel that creates thin walls recommends using only 20 Newton centimeters. The Nobel Active and Implant Direct's interactive implants have a 78-degree lead-in bevel in contrast to the 45-degree lead-in bevel of the original screw vent connection replicated in Implant Direct's legacy implant system. When you have a long, steep bevel, the walls get thinner and the hex gets deeper. When the Nobel Active was first launched in 2008, shortly after my internal conical connection patent expired, the company recommended that X-rays be taken to confirm that the abutment was fully seated. Straumann recently introduced the BLX implant with an 84-degree lead-in bevel, but they had the good sense to keep it relatively short. It is generally accepted that internal conical connections with lead-in bevels are the preferred design because of the stability between mating parts. All of the abutments for implants with lead-in bevels should be made with a half-degree less taper to ensure contact at the opening of the internal shaft. This graphic of a pal-top connection demonstrates this fact. Therefore, having a steeper or longer taper to the implant's bevel does not contribute to greater stability. This picture of a cross-section of a Neodent Grand Morris implant with its 74-degree taper demonstrates what happens if the first point of contact is down the bevel and not at the opening of the internal shaft of the implant. A gap is created at the opening of the shaft. A Morris taper is 1 to 1.5 degrees, not 16 degrees as used by the Neodent implant. This slide shows a case using the Astra implant, which has a long 80-degree internal bevel. Tightening the fixation screw to seat the long bevel of the abutment results in lateral forces on the thin walls of the implant, which is why this company only recommends 15 to 25 Newton centimeters of torque for tightening fixation screws, depending on the diameter of the implant. As shown here in these follow-up X-rays, the lateral forces on the thin walls of the implant resulted in part of the implant's wall fracturing. This resulted in a loosening of the abutment and significant bone loss, with the ultimate removal of the implant. What is the best implant surface has been a question for debate since the early 1980s. With Nobel selling smooth machined surface implants, Straumann selling rough, porous titanium plasma sprayed surface implants, and Corvent selling implants with a textured surface created by aluminous oxide blasting followed by hydrofluoric acid etching. By 1991, Corvent started blasting its implants with hydroxylapatite crystals, creating a medium rough surface without the necessity to acid etch to remove particles. The machined surface Nobel implants proved to be too smooth for good success in soft bone. In about 2004, Nobel introduced Tyounite, a rough, porous surface created by anodizing. Straumann abandoned its rough, porous TPS surface in the late 1990s, replacing it with large grit aluminous oxide blasted surface followed by acid etching, which was referred to as SLA. Straumann subsequently introduced a premium-priced version of this surface called SL Active. This consisted of packaging the SLA surfaced implants in sterile saline to isolate it from carbon deposits from the atmosphere until the time of insertion. Straumann claimed this improved bone attachment by making the surface more hydrophilic. Implant Innovations promoted its OsseoTite acid-etched surface, which was even smoother than the machine surface. Calcitech in the late 1980s promoted a low crystalline HA-coated surface coated to the top of their cylindrical implant. That was essentially replaced with a high crystalline HA surface. All of these early blasted surfaces of Straumann, Corvent, and Astra have stood the test of time, as have the HA-coated surfaces. Nobel just modified its Tyounite implants by anodizing the top few millimeters of the implant, creating a very smooth surface to minimize complications from exposed Tyounite. Nobel posted on its website this meta-analysis of studies reporting favorably on its Tyounite surface by Dr. Albrechtsen, one of its paid non-dental opinion leaders. The results of 106 studies, according to Albrechtsen, showed only 5% of the patients had peri-implantitis. I always questioned Albrechtsen's veracity after I uncovered in the late 1980s that he and Branemark, in a 1983 article, had misrepresented as an osteoblast an SEM of a fibroblast that had appeared in a 1982 article. That same phony picture later appeared colorized on the cover of Branemark's textbook. If the Tyounite rough porous surface does not contribute to soft tissue complications and subsequent bone loss, then one might ask why Nobel is now replacing Tyounite on the top few millimeters of its implants with a smoother anodized surface. Here is a copy of an email sent by a periodontist in Toronto to some Nobel sales representatives, and for some reason he copied me on it. He is telling these Nobel reps that at least 25% of his cases with Nobel-replaced Tyounite implants are showing, quote, an unacceptably high degree of early bone loss, end of quote. So where does the truth lie? I think you want to have a medium rough textured surface and you want to carry it to the top of the implant. If you have very porous bone and you want to use an implant surface that will improve your chances of success, HA coating should be considered, although not necessary with the soft bone surgical protocol incorporated into the legacy and screw-vent implant systems. About a decade ago, Nobel's one-piece Nobel Direct implant was sold with the porous Tyounite surface extending up the neck into the soft tissue area. Nobel claimed this promoted, quote, soft tissue integration, end of quote. That implant was eventually taken off the market after a class action lawsuit was filed by a dentist who had multiple failures with this implant. Apparently, Nobel's answer now is to create a smooth surface on the top few millimeters of the implant by anodizing, while claiming that this creates muco-integration. The grooves at the top of the Nobel Active are there because that area is intended to be, and hopefully remain, subcrestal. Anodizing the neck makes it smoother than just leaving it as a machine surface, and we know that the Branemark machine surface implant often experience bone loss to the first thread. The only rationale to color the neck gold would be if resorption took place, exposing it to the soft tissue, and then only in the aesthetic zone. From the reference to, quote, mucointegration, end of quote, it sounds like Nobel anticipates bone loss from this implant, resulting in the gold neck being exposed to the soft tissue. Certainly, there is no rationale for a gold-colored neck in the posterior, and especially not on an all-on-4 case as shown here. These studies from the late 1980s, comparing all 4 surfaces used by Corvent, shows that by 2 months, HA-coated screw vent implants doubled the attachment strength as measured by torque removal. By the early 1990s, SBM replaced acid etch and TPS surfaces on Corvent implants. The same SBM surface is being used today by Implant Direct, BioHorizons, and Zimmer Biomet. Zimmer Biomet is promoting the trabecular metal surface screw vent as a premium price with a trabecular metal insert in its midsection. This eliminates about 2/3 of the thread engagement and provides a porous surface that could become a hygiene problem if exposed from bone loss. Initially, Zimmer had an FDA recall on this implant, requiring that it change the surgical protocol in dense bone to eliminate thread engagement by the apical threads of the implant. When the apical threads engaged bone, the threaded part below the trabecular metal was separating from the implant. The reason was that they slipped this trabecular metal on the implant core and then weld the bottom threaded portion. Using step drills, this apical threaded portion would engage dense bone and break off as the implant continued to be turned. From this X-ray, it appears that the implant has been changed from tapered to straight, giving up on the advantages of bone compression from inserting a tapered implant into an undersized socket. Straumann claims that delivering its implant in a vial filled with sterile saline will make the surface more hydrophilic and that this will reduce healing time. The question is whether there is any clinical advantage to this packaging variation that can justify the extra $67 Straumann charges in the US. Straumann relies on studies showing that SL-active implants were successful when loaded at 4 weeks, but these studies did not use a control of the same implant loaded immediately, which also may have shown high success. Another unique selling proposition of Straumann implants is its use of titanium zirconium alloy called rock solid rather than titanium 6Al4V alloy used by most other implant companies and the orthopedic industry. Titanium zirconium alloys are more brittle and therefore potentially more likely to fracture. This Boozer study in mini pigs comparing SLA to SL-active surfaces on Straumann implants shows that torque removal during the 3rd to 4th week following implantation of an SL-active implant did not dip as much as the SLA surface implants. Both initially and by the 8th week, there was no difference in torque removal. This chart from a Zimmer dental study compared primary stability achieved with its tapered screw vent implant to that of the Nobel Active, Nobel Replace, and Straumann straight bone level implants. It generated 100% more than Straumann's implant. From a clinical standpoint, achieving high initial torque allows for immediate loading of the implant. What the torque values are at the 3rd to 4th week after implantation is of little consequence. You're either going to get enough initial torque to load the implant immediately, or you're going to leave it for 8 to 12 weeks and let healing occur before placing the implant into function. Far more important is the relationship between the implant design and its surgical protocol in achieving high initial stability to allow immediate loading even in soft bone. These pictures show blood running up SBM and HA-coated implant direct implants. So claims of unique advantages by Straumann of its hydrophilic implant surface have never been clinically proven. This slide demonstrates the disadvantages of subcrestal placement of implants. While this can be done with any two-piece implant, the Morse taper connection of the ankylose and bicon implants often requires subcrestal placement in order to drop the height of contour of the abutment below the soft tissue for aesthetics. This is because their friction-fit abutments emerge from the implant as a narrow post and require several millimeters of length to create an acceptable emergence profile. Subcrestal placement sacrifices at least 2 millimeters of crestal bone support and creates an infrabony defect. I've simulated graphically what a more natural emergence profile would look like if an implant with a screw-retained abutment was placed level with the crest of the ridge. This bicon implant was placed about 3 millimeters below the crest of the bone. With this type of placement, a contouring drill is often needed to remove crestal bone in order to seat the abutment. The case on the right, using a Legacy 4 implant placed subcrestal, shows that the use of an older healing collar without a concave neck failed to fully seat. It was replaced with the healing collar provided free with the implant. A recent study by Selena et al. In the International Journal of Oral Implantology, 2019, Volume 12, confirmed that placing an implant 1.5 millimeters subcrestal compared to only 0.5 millimeters demonstrated no improvement in aesthetics or clinical difference in bone loss. Doing so can obviously complicate attachment of healing collars and abutments. Platform switching describes the use of an abutment of smaller diameter than that of the implant platform to medialize the implant abutment margin, a design that some claim reduces bone loss. Such a ledge is inherent with internal connection implants having a lead-in bevel because of the wall thickness needed to support the abutment. This randomized clinical trial concluded that, quote, it could not confirm the hypothesis of a reduced peri-implant bone loss at implants restored according to the concept of platform switching, end of quote. This slide shows the use of length-specific taper drills with the Neodent and Nobel Replace system of tapered implants. This requires that the final sizing drill need to be both length-specific and diameter-specific for each implant, adding significantly to the number of drills. The use of straight step drills with score lines and increasing the diameter of the drills depending on the density of the bone reduces the number of drills needed to insert a tapered implant, such as the Screwvent and Legacy implants. In very dense bone, a crestal bone drill is used to open the top of the socket to match the diameter of the implant neck. Using step drills with score lines for insertion of tapered implants dramatically reduces the number of drills needed. Many screw implant systems, whether tapered or straight, include bone taps for creating threads in dense bone. Implant Direct does not need to make bone taps for its tapered implants for several reasons, including the strength of its internal hex connection, the efficiency of its self-tapping grooves, and its surgical drill protocol. In very dense bone, the final sizing drill is just slightly smaller than the diameter of the implant, and crestal bone drills are provided to enlarge the top of the socket to match the diameter of the neck of the implant in very dense bone. This slide shows a fractured Nobel Replace implant being removed and the warning label on the Nobel Replace implant vial not to exceed 45 Newton centimeters of torque during insertion. This is due in part to the wall thickness and in part to the use of commercially pure titanium rather than titanium alloy used by most other implant manufacturers. This is because Nobel's Ti-Unite surface, created by anodizing, apparently will not form on an alloy surface. This Nobel ad shows a bird nestled in an exhaust pipe to make the point that just because something fits doesn't mean it works. The ad also shows an SCM of a fractured Nobel active implant and implies that the fracture was caused by the use of mismatched competitors' abutments. Implant Direct received FDA marketing approval to claim compatibility of its replant and interactive abutments by demonstrating that it had accurately reverse engineered the internal connection of the Nobel Replace and Nobel Active implants. Certainly, after Danaher acquired 100% of Nobel and Implant Direct, and Implant Direct is under the management of Nobel executives, Nobel could share engineering drawings to confirm the compatibility if it had any real concerns. Instead, Nobel's management has deleted any Implant Direct marketing materials, catalogs, and videos referencing prosthetic compatibility with Nobel implants in order to preserve sales of its more expensive Nobel abutments. Both Straumann and Nobel advise against the use of aftermarket compatible abutments with their implants. Yet Straumann acquired Medentika and sells abutments for its competitors' implants, and Nobel sells CAD-milled abutments for its competitors' implants. In conclusion, from 1982 to 2017, I've been issued 33 U.S. patents related to dental implants. Just a couple of sayings that relate to the process of inventing new products. Discovery consists of seeing what everybody has seen and thinking what nobody has thought. Also, the greatest obstacle to discovery is not ignorance, it is the illusion of knowledge. When you think you know it all, you just stick with what you know. Thank you very much.